Alright, so I don't actually think I need Visual Studio Code for this. I think I'm just watching a video. This isn't actually part of the weeks, so I believe I don't actually am required to do this, but because I'm doing this because I just want the knowledge, I'm obviously going to watch it. Let's see. I was debating about doing this at the end after maybe finishing everything, because I did just finish week 7. I just have these 2 weeks, and then week 10 is the end. I'm supposed to do one final project. But with this being right here, I was thinking about maybe doing it at the end, but then I was like, well, if they wanted you to do it at the end, then I feel like they would have put it at the end, but they put it here, and I feel like there's a reason for that, so I'm going to just kind of assume that there is a good reason for it being here. And here, I actually don't think I need this. If I do, I'll bring it up, screw it. If I actually use anything, which I don't know if I will. So I believe that this is just going to be a video. I kind of skimmed through it to see what it's about. It's only less than an hour long. I have time, so let's go ahead and get this into. I don't know how complex this is. I know AI encoding is supposed to be like ridiculous, but here we go. Now, in case anyone's wondering, by the way, why I'm even streaming this, because I have an interest. Maybe there's people that share that interest. Maybe there's people that have information. You know, we're all just trying to do something. So it's not nothing too crazy about it. Just, and it shows me how much time I'm putting into learning this stuff. So I have like a log of, basically I have my own log of the hours I'm putting into learning coding. So. Oh, there it goes. Let's see.
This is CS50, and this is our lecture on artificial intelligence, or AI, particularly for all of those family members who are here in the audience with us for the first time. In fact, for those students among us, maybe a round of applause for all of the family members who have come here today to join you. Nice. So nice to see everyone, and as CS50 students already know, it's sort of a thing in programming circles to have a rubber duck on your desk. Indeed, a few weeks back, we gave one to all CS50 students, and the motivation is to have something to talk to in the presence of a bug or mistake in your code or confusion you're having when it comes to solving some problem. And the idea is that in the absence of having a friend, family member, TA of whom you can ask questions, is to literally verbalize your confusion, your question, to this inanimate object on your desk. And in that process of verbalizing your own confusion and explaining yourself, quite often does that proverbial light bulb go off over your head, and voila, problem is solved. Now, as CS50 students also know, we sort of virtualized that rubber duck over the past few years, and most recently in a form of this guy here. So in students' programming environment within CS50, a tool called Visual Studio Code at a URL of cs50.dev, they have a virtual rubber duck available to them at all times. And early on, in the very first version of this rubber duck, it was a chat window that looked like this. And if students had a question, they could simply type into the chat window something like, "I'm hoping you can help me solve a problem." And for multiple years, all the CS50 duck did was respond with 1, 2, or 3 quacks. We have anecdotal evidence to suggest that that alone was enough for answering students' questions, because it was in that process of like actually typing out their confusion that you realize, oh, I'm doing something silly, and you figure it out on your own. But of course, now that we live in an age of ChatGPT and Claude and Gemini and all of these other AI-based tools, Came as no surprise, perhaps, when in 2023, this same duck started responding to students in English. And that now is the tool that they have available, which is, in effect, meant to be a less helpful version of ChatGPT. One that doesn't just spoil answers outright, but tries to guide them to solutions akin to any good teacher or tutor. And so today's lecture is indeed on just that, and the underlying building blocks that make possible that there rubber duck and all of the AI with which we're all increasingly familiar, namely generative artificial intelligence, using this technology known as AI to generate something, whether that's images or sounds or video or text. And in fact, what we thought we'd do to get everyone involved early on is if you have a phone by your side, if you'd like to go ahead and scan this QR code here, and that's going to lead you to a polling station where you can buzz in with some answers. CS50's preceptor Kelly is going to kindly join me here on stage to help run the keyboard. And what we're about to do is play a little game and see just how good we humans are right now at distinguishing AI from reality. And so we'll borrow some data from the New York Times, which a couple years back actually published some examples of AI and not AI, and we'll see just how good this technology has gotten. So here we have two photographs on the screen. In a moment, you'll be asked on your phone, if you were successful in scanning that code, which one of these is AI, left or right? So hopefully on your phone here, if you want to go ahead and swipe to the next screen, we'll activate the poll here. In a moment, you should see on your phone a prompt inviting you to select left or right.
Say right.
Feel free to raise your hand if you're not seeing that. But it looks like the responses are coming in, and at the risk of spoiling, it looks like 70% plus of you think it is the answer on the right. And if Kelly, maybe we could swipe back to the two photographs. In this particular case, yes, it was in fact the one on the right. Maybe it looked a little too good, or maybe a little too unreal. Maybe, let's see, maybe a couple of other examples. So same QR code, no need to rescan. Let's go ahead and pull up these two examples now. Two photographs, same question. Which of these is AI?
I would say left.
Or right? Left or right?
I'd say left.
All right, want to take a look at the chart, see what the responses are coming in. A little closer in this case, but a majority of you think the answer is in fact left here, though 5% of you are truthfully admitting that you're unsure. But Kelly, if you want to swipe back to the photos, the answer this time was in fact a trick question. They were both in fact AI.
Oh, crap.
Perhaps speaks to just how good this technology is already getting. Neither of these faces exists in the real world. It was synthesized based on lots of training data, so two photographs that look like humans, but do not in fact exist. How about one more, this time focusing on text, which will be the focus, of course, underlying our duck. Did a fourth grader write this or the new chatbot? Here are two final examples. Same code as before, so no need to rescan. And here are the texts. Essay 1. I like to bring a yummy sandwich and a cold juice box for lunch, and sometimes I'll even pack a tasty piece of fruit or a bag of crunchy chips. As we eat, we chat and laugh and catch up on each other's day. ... Essay 2. My mother packs me a sandwich, a drink, fruit, and a treat. When I get into a lunchroom, I find an empty table and sit there and eat my lunch. My friends come and sit down with me. ... The question now, lastly, is which of these is AI? One or two? Essay 1 or 2? The bars here are duking themselves out. It looks like a majority of you say essay 1. Let's go back to the text, and one of you who says essay 1, why? If you want to raise a quick hand. Why essay 1? Yeah.
Just the way it's too
Okay, and so essay 2 looks more like you would, right? And can I ask what grade you are in? Oh, 5th grader. So is this a new 5th grader or not? The answer here, in fact, is that essay 1 is the AI, because indeed essay 2 is more akin to what a 4th, or if I may, a 5th grader would write. And I dare say there are maybe some telltale signs. I'm not sure a typical 4th grader or 5th grader would catch up on each other's day in the vernacular that we see in essay 1. But suffice it to say, this game is not something we can play in the years to come, because it's just going to get too hard to discern something that's AI generated or not. And so among our goals for today is really to give you a better sense of not just how technologies like this duck and these games that we've played here with images and text work, but really what are the underlying principles of artificial intelligence that frankly have been with us and have been developing for decades and have really now come to a head in recent years, thanks to advances in research, thanks to all the more cloud computing, thanks to all the more memory and disk space and information, sheer volume thereof that we have at our disposal that can be used to train all of these here technologies. So that there duck is built on a fairly complicated architecture that looks a little something like this, where here's a student using one of CS50's tools, here's a website with which CS50 students are familiar called CS50.ai, where we, the staff, wrote a bunch of code that actually talks to what are called APIs, application programming interfaces, third-party services by companies like Microsoft and OpenAI that really have been doing the hard work of developing these models, as well as some local some local sauce that we CS50 add into the mix to make it specific, the duck's answers to CS50 itself. But what we've essentially been doing is something that with which you might be familiar, in part, prompt engineering, which has started popping up, for better or for worse, on LinkedIn profiles everywhere. And prompt engineering, really, it's not so much a form of engineering as it is a form of asking good questions and being detailed in your question, giving context to the underlying AI so that the answer with high probability is what you want back. And so there's two terms in this world of prompt engineering that are worth knowing about. So CS50 has leveraged both of these to implement that duck. We, for instance, wrote what's called a system prompt, which are instructions written by us humans, often in English, that sort of nudge the underlying AI technology to have a certain personality or a specific domain of expertise. For instance, we, CS50, have written a system prompt essentially that looks like this. In reality, it's like a lot of lines long nowadays, but the essence of it is this. You are a friendly and supportive teaching assistant for CS50. You are also a rubber duck. And that is sufficient to turn an AI into a rubber duck, it turns out. Answer student questions only about CS50 in the field of computer science. Do not answer questions about unrelated topics. Do not provide full answers to problem sets, as this would violate academic honesty. Answer this question, colon. And after that preamble, if you will, aka system prompt, we effectively copy-paste whatever question a student has typed in, otherwise known as a user prompt. And that is why the duck behaves like a duck in our case, and not a cat or a dog or a PhD, but rather something that's been attenuated to the particular goals we have pedagogically in the course. And in fact, those of you who are CS50 students might recall from quite some weeks ago in week 0, when we first introduced the course to the class, we had code that we whipped up that day that ultimately looked a little something like this. And I'll walk through it briefly, line by line, but now, on the heels of having studied some Python in CS50, this here code that I whipped up in the first lecture might make now a bit more sense. In that first lecture, we imported OpenAI's own library, code that a third-party company wrote to make it possible for us to implement code on top of theirs. We created a variable called client in week 0, and this gave us access to the OpenAI client, that is software that they wrote for us. We then defined in week 0 a user prompt, which came from the user using the input function with which CS50 students are now familiar. And then we defined this system prompt that day where I said, limit your answer to one sentence, pretend you're a ... cat, I think was the persona of the day. And then we used some bit more...
Yeah, let's hold on. I don't remember that. That was in week 0? Let's see. Okay. What was it called? Chat.py. No, I do not have one like that. But let's go ahead and type this bad boy up, because why not? Adds to... Alright. Let's try this out. This is using Python. Okay, so we are from OpenAI import. Right, client equals OpenAI user prompt equals input. I want to get this stuff taken care of, right? System prompt equals limit your answer to one sentence. Pretend you're a duck. Okay, hold on, watch. I'm gonna put this whole thing down. So this is how you create. This is, okay, hold on. This is kind of crazy.
Answer student questions only about CS50 in the field of computer science. Do not answer questions about unrelated topics. Do not provide full answers to problem sets, as this would violate academic honesty. Answer this question, colon. And after I studied some Python in CS50,
Pretend you're, this is the one where it's a cat, right?
this here code that I whipped up in the first lecture might make now a bit more sense. In that first lecture, we imported OpenAI's own library, code that a third-party company wrote to make it possible for us to implement code on top of theirs. We created a variable called client in week 0, and this gave us access to the OpenAI client, that is software that they wrote for us. We then defined in week 0 a user prompt, which came from the user using the input function with which CS50 students are now familiar. And then we defined this system prompt that day where I said, limit your answer to 1 sentence, pretend you're a ... cat, I think was the persona of the day. And then we used some bit more arcane code here, but in essence, we created a variable called response, which was meant to represent the response from OpenAI's server. We used client.responses.create, which is a function or method that OpenAI gives us that allows us to pass in 3 arguments. The input from the user, that is the user prompt, the instructions from us, that is the system prompt, and then the specific model or version of AI that we wanted to use. And the last thing we did that day was print out response.output_text. And that's how we were able to answer questions like, what is CS50 or the like. So we've seen all of that before, but we didn't talk.
Okay.
Talk about that week exactly how it was working or what more we could actually do with it. And so in fact, what I thought we'd do today is peel back a layer that we've not allowed into the course up until now. And indeed, you still cannot use this feature until the very end of the class in CS50 when you get to your final projects, at which point you are welcome and encouraged to use VS Code in this particular way. So here again is VS Code. For those unfamiliar, this is the programming environment we use here with students. And let me open up some code that was assigned to students a couple of weeks back, namely a spell checker that they had to implement in C. So I came in advance with a folder called Speller. And inside of this folder, I had code that day, and all students had that week, called dictionary.c. And in this file, which will not look familiar to many of you if you've not taken week 0 through 7 up until now, we did have some placeholders for students. So long story short, students had to answer a few questions, that is write code to do this to do, this to do, this to do, and one more. There were 4 functions or blanks that students needed to fill in with code, and I dare say it took most students 5 hours, 10 hours, 15 hours, something in that very broad range. Let me show you now how using AI, you, soon the aspiring programmers, can start to write code all the more quickly, not by just choosing a different language, but by using these AI-based technologies beyond the duck itself. So what I've done here on the right-hand side of VS Code is enabled a feature that CS50 disables for all students from the start of the course called Copilot. This is very similar in spirit to products from Google and Anthropic and other companies as well, but this is the one that comes from Microsoft and in turn GitHub here, and it too gives us me sort of a chat window here, and this is just one of its features. For instance, if I wanted to implement, to get started, the check function, I could just ask it to do that. Implement the check function, and how about using a hash table in C? I'm going to go ahead and click enter. Now it's going to work. It's using as reference, that is context, the very file that I've opened, which is dictionary.c here.
It's super helpful.
Copilot in general, as well as a lot of AI tools, are familiar with CS50 itself because it's been freely available as open courseware for years. What you see here doing is essentially thinking, though that's a bit of an overstatement, it's not really thinking, it's trying to find patterns in what the problem is I want to solve among all of its training data that it's seen before and come up with a pretty good answer. So for today's purposes, I'm going to wave my hand at the ChatGPT-like explanation of what to do that has appeared at right, but what's juiciest to look at here is on the left, if I now scroll down, is highlighted in green is all of the suggested code for implementing this here check function. Now, it might not be the way you implemented it yourself, but I do dare say this has hints of exactly what you probably did when it came to implementing a hash table. And in fact, I can go ahead and keep all of this code if I like how it looks. Let's assume that's all correct there. It might be the case that I want to now implement the load function. So how about now implement load function, enter. As simple as that. And what data is being used? Well, a few different things. It says one reference, so it's indeed using this one file, but there's also what are called comments in the code with which all students are now familiar, these / commands in gray that are giving English hints as to what this function is supposed to do. There's implicit information as to what the inputs to these functions, otherwise known as arguments, are meant to be, what the outputs are meant to be. So the underlying AI, called Copilot here, kind of has a decent number of hints. And much like a good TA or a good software engineer, that's enough context to figure out how to fill in those blanks. And so here too, if I scroll down now, we'll see in green some suggested code via which it could solve that same problem as well, the load function. And I dare say I've been talking for far fewer minutes than CS50 students spent actually coding the solution from scratch to this here problem. So I'll go ahead and click keep. I'll assume that it's correct, but that's actually quite a big assumption. And those of you wondering, like, why have we been learning all this if I could just ask in English it to do my homework for me? I mean, there's a lot to be said for the muscle memory that hopefully you feel you've been developing over the past several weeks. The reality is if you don't have an eye for what you're looking at, there's no way you're going to be able to troubleshoot an issue in here, explain it to someone else, make marginal changes or the like. And yet, what's incredibly exciting, even to someone like me, all of the staff, friends of mine in the industry, is that this kind of functionality in AI amplifies your capabilities as a programmer sort of overnight. Once you have that vocabulary, that muscle memory for doing it yourself, the AI can just take it from there and get rid of all of the tedium, allow you to focus at the whiteboard with the other humans on sort of the overarching problems that you want to solve, and leave it to this AI to actually solve problems for you. A fun exercise too might be to go back at term's end and try solving any number of the course's assignments. For instance, let me go ahead and do this. In my terminal window here, I'm going to go back to my main directory. I'm going to create an empty file called mario.c that has nothing in it. And I'm going to go ahead in my chat window here and say, please implement a program in C that prints a left-aligned pyramid of bricks using hash symbols for bricks, and use the CS50 library to ask the user for a non-negative height as an integer, period. I dare say that's essentially the English description of what was, for CS50 this year, problem set 1 to implement a program called mario.c. This too is sort of doing its thing. It's using one reference, it's working. It knows as a hint that this file is called mario.c, and it's seen a lot of those in its training data over time. There's an English explanation of what I should do, and those CS50 students in the room probably recognize the sort of basic structure here of using a do-while loop to prompt the user for a height, using the CS50 library, which has been included, print a left-aligned pyramid using some kind of loop, and boom, we are done. And these are fairly bite-sized problems, as you'll see as you get to term's end with your final project, which is a fairly open-ended opportunity to apply your newfound knowledge and savvy with programming itself to a problem of interest. It will allow you to implement far grander projects, far greater projects than has been possible to date, certainly in just the few weeks we have to do it, because of this amplification of your own abilities. So with that promise, let's talk about how in the heck any of this is actually working. I clearly just generated a whole lot of stuff, and that's how we began the story, with the generation of those images and those 2 essays by kids. But what is generative artificial intelligence, or really, what is AI itself? And these are some of the underlying building blocks that aren't going anywhere anytime soon, and indeed have led us as a progression to the capabilities you just saw. So spam, we sort of take for granted now that in our Gmail inboxes or Outlook inboxes, most of the spam just ends up in a folder. Well, there's not some human at Microsoft or Google sort of manually labeling the messages as they come in, deciding spam or not spam. They're figuring out using code, and nowadays using AI, that looks like spam, and therefore I'm going to put it in the spam folder, which is probably correct 99% of the time, but indeed there's potentially a failure rate. Other applications might include handwriting recognition. Certainly Microsoft and Google doesn't know the handwriting style of all of us here in this room, but it's been trained on enough other humans' handwriting styles that odds are your handwriting and mine looks similar to someone else's, and so with very high probability, they could recognize something like hello world here as indeed that same digital text. All of us are into streaming services nowadays, Netflix and the like. Well, they're getting pretty darn good at knowing if I watched X, I might also like Y. Why? Well, because of other things I've watched before and maybe upvoted and downvoted, maybe because of other things people have watched who like similar movies or TV shows to me. So that too is AI. There's no if else construct for every movie or TV show in their database. It's sort of figuring out much more organically, dynamically, what you and I might like. And then all these voice assistants today, Siri, Alexa, Google Assistant, and the like, those too don't recognize your voice or necessarily know what questions you're going to ask it. There's no massive if-else if that has all possible questions in the world just waiting for you or me to ask it. That too, of course, is dynamically generated. But that's getting a bit ahead of ourselves. Let's rewind in time, and some of the parents in the audience might remember this here game, among the first arcade games in the world, namely Pong. And so this was a black and white game whereby there's two players, a paddle on the left, a paddle on the right, and then using some kind of joystick or trackball, they can move their paddles up and down, and the goal is to bounce the ball back and forth, and ideally catch it every time. Otherwise, you lose a point. This is just an animated GIF, so there's nothing really dramatic to watch. It's going to stay at 15 against 12, just looping again and again. Nothing interesting is going to happen, but this is a nice example of a game that lends itself to solving it with code. And indeed, it's been in our vernacular for years to play against not just the computer, but the CPU, the central processing unit, or really the AI. And yet AI does not need to be nearly as sophisticated as the tools we now see. For instance, here's a successor to Pong known as Breakout, similar in spirit, but there's just one paddle and one ball, and the goal is to bounce the ball off of these colorful bricks, and you get more and more points depending on how high up you can get the ball.
Had the big old
All of
wheel.
us as humans, even if you've never played this old school game, probably have an instinct as to where we should move the paddle. If the ball just left it going this way, which direction should I move the paddle?
To the left.
I mean, probably to the left, and indeed, that'll catch it on the way down. So you and I just made a decision that's fairly instinctive, but it's been ingrained in us, but we could sort of take all the fun out of the game and start to quantify it or describe it a little more algorithmically, step by step. In fact, decision trees are a concept from economics, strategic thinking, computer science as well. That's one way of solving this problem in such a way that you will always play this game well if you just follow this algorithm. So for instance, how might we implement code or decision-making process for something like Breakout? Well, you ask yourself first, is the ball to the left of the paddle? If so, you know where we're going, then go ahead and move the paddle left. But what if the answer were no, in fact? Well, you don't just blindly move the paddle to the right, probably. What should you then ask?
Is the ball to the right?
Are you right below the ball? If the ball's coming right at you, you don't want to just naively go to the right and then risk missing it. So there's another question to ask. Is the ball to the right of the paddle? And that's a yes-no question. If yes, well then, okay, move it to the right. But if not, you should probably stay exactly where you are and don't move the paddle. All right, so that's fairly deterministic, if you will. And we can map it to code using pseudocode in say a class like CS50. We can say in a loop, well, while the game is ongoing, if the ball's to the left of the paddle, then move the paddle left.
This one I don't got to do any problem sets for. I don't really have to technically do this, but it's about artificial intelligence, and I'm already halfway through it. It's only like 47 minutes, so I figured I was going to go ahead and check it out and see what knowledge I can get out of it. So far, it hasn't taught me anything new, but hey. What's up? Did you need something? You want a hug? I can give you a hug.
I'm having a rough go at it.
Oh, the classes?
Just everything right now.
Oh.
I love you. Thank you.
Huh?
Thank you. I love you.
I love you too.
How's your class thing going?
I'm halfway through it, and it hasn't really taught me anything new. It would have if I've never used Visual Studio, but I've already used Visual Studio, and all it's talking about is Visual Studio has a AI chat that you can use to help you do the codes. And he's like, well, why are we teaching you how to do code if you can just use the AI to build the code? And he's like, because if you can't see it and read it, then how are you going to build upon it? Because the AI can't build it, but it needs your instructions. So the idea is you use AI to do all the hard work for you, but you and your team can focus on the bigger picture.
Oh.
Yeah.
I like that he gave an extra little something on the side.
Yeah. So, yuppers.
Thank you, babe.
Mm-hmm.
Love you.
Love you too.
222.
222. No, the time. Yeah, I should be able to finish this in time. Stop what? Hey, Jim. This is just a video. I think this is all I got, but we'll see. She's not feeling good. Sick day. But
Else, if the ball's to the right of the paddle, sorry for the typo there, move the paddle right. Else, just don't move the paddle. And so these decision trees, as we drew it, have a
she's been studying the realtor classes, so that's what she's been trying to do is her realtor stuff while I've been doing this stuff. And the realtor stuff, arguably, I feel like is harder because she has the learn. Well, you're back.
What?
Are you okay?
No.
Yeah, you can stay in here if you want. Your phone died?
Nah, a little bit. I just want to take my uterus out and like put it somewhere. Is that an option?
Well, I wasn't gonna say that. I'm streaming, but I wasn't gonna say that. I just said that you were sick.
I'm on my lady days. It's rough, y'all.
Oh man.
It makes me emo. Okay, I need cuddles.
Oh, he said, "Can you say hi for me?" I don't know if he's talking to me or you.
Oh, hi.
Hi.
Ow.
Hi.
Oh, more hug and I'll leave you alone.
Okay. I mean, you can chill if you want.
I gotta do my classes.
Well, I mean, you keep getting distracted from it, but
I just need chocolate. And
chocolate.
love.
I mean, we have chocolate.
I know, I'm making more chocolate. It's okay. 2 more days.
It sounds like your nose is running now too.
It's my sinuses.
Mm.
It's because I have low iron already. And so with low iron, do you want some dark chocolate?
No, I still got my other chocolates, the fancy ones. Ow.
Okay, I see chocolates too. I bit into all of them, so I already know what's left in there.
God, you're so weird.
You like my weird?
Okay. Alright. I'm gonna try to finish this before Corey gets out.
Love you.
Love you too. Alright.
perfect mapping to code, or really pseudocode in this particular case, which is to say that's how people who implemented the breakout game or the Pong game who implemented a computer player surely coded it up. It was as straightforward as that.
Yeah.
But how about something like tic-tac-toe, which some of you might have played on the way in for just a moment on the scraps of paper that you might have had.
Yeah,
Here we have a
bit more
tic-tac-toe
complex.
board with two O's and two X's. For those unfamiliar, this game, tic-tac-toe, otherwise known as Knights and Crosses, is a matter of going back and forth, X's and O's, between two people, and the goal is to get 3 O's in a row or 3 X's in a row, either vertically, horizontally, or diagonally. So this is a game here in mid-progress. Well, let's consider how you could solve the game of tic-tac-toe like a computer, like an AI might. Well, you could ask yourself, can I get 3 in a row on this turn? Well, if yes, well, play in the square to get 3 in a row. It's as straightforward as that. If you can't, though, what should you ask? Well, can my opponent get 3 in a row on their next turn? Because
How? You were chilling in there that whole time. Are you serious? Yeah. Okay, got one.
if so, you should probably at least block their move next, so at least you don't lose now. But this game, tic-tac-toe, is relatively simple as it is, gets a little harder to play when it's not obvious where you should go. Now, all of us as humans, if you grew up playing this game, probably had heuristics you used, like you really like the middle, or you like the top corner, or something like that. So we probably can make our next move quickly, but is it optimal? And I dare say, if back in childhood or more recently, you've ever lost the game of tic-tac-toe, like you're just bad at tic-tac-toe, because logically there's no reason you should ever lose a game of tic-tac-toe if you're playing optimally. At worst, you should force a tie, but at best you should win the game. So think of that the next time you play tic-tac-toe and lose, like you're doing something wrong, but in your defense, it's because the question mark is sort of non-obvious. Like, how do I answer it when the answer is not right in front of me to move for the win or move for the block? Well, one algorithm you could have been using all of these years is called minimax. And as the name suggests, it's all about minimizing something and or maximizing something else. So here too, let's take a bit of fun out of the game and turn it into some math, but relatively simple math. So here we have 3 representative tic-tac-toe boards. O has one here, X has one here, and the middle is a tie. Doesn't matter how we score these boards, but we need a consistent system. So I'm going to propose that anytime O wins, the score of the game is -1. Anytime X wins, the score of the game is a +1. And anytime nobody wins, the score is 0. So at this point, each of these boards have these values, -1, 0, and 1. So the goal, therefore, in this game of tic-tac-toe now is for X to maximize its score, because 1 is the biggest value available, and O's goal in life is to minimize its score. So that's how we take the fun out of the game. We turn it into math, where one player just wants to maximize, one player just wants to minimize their score. All right, so a quick sanity check here. Here's a board. It's not color-coded. What is the value of this board? 1, because X has, in fact, 1 straight there down the middle. So X is 1, O is -1, otherwise a tie. So now let's see how we go about, with those principles in place, figuring out where we should play in tic-tac-toe. Now here's a fairly easy configuration. There's only 2 moves left. It's not hard to figure out how to win or tie this game, but let's use it for simplicity. It's O's turn, for instance, so where can O go? Well, that invites the question, well, what is the value of the board, or how do we minimize the value of the board for O to win? Well, O can go in one of 2 places, top left or bottom middle. Which way should O go? Well, if O goes in top left, we should consider what's the value of this board. Is it minimal? Well, let's see. If O goes here, X is obviously...
Well, I mean, it is called the Introduction to Computer Science, so yeah, it's not... I wasn't sure exactly what route he was going to go down with this, because they have a course for AI specifically that goes in further detail, but I heard it's really freaking hard. Can you say for me to your kid? What? I don't know what you're asking. But yeah, I mean, it's still, it's still interesting. I mean, knowing how the basics work. That's what he's been doing with everything. He's been starting from the very basic, from square one, like if you never heard anything about it, and then working from there, so. Yeah. Yeah. Oh, yeah, no, I wasn't saying that you were saying that it was bad. I just, probably, I don't know. I'm just saying, yeah, that's kind of the reason I've been taking these and watching these, is because he's been literally explaining it like to a beginner, and so it's, I don't know, a lot of the other things that I was getting into is kind of just diving into it without, going back and explaining everything, and that's the other reason I've been doing all these, just because they're definitely, but yeah. No, I got you. I know you weren't trying to say it was bad or nothing, but yeah. Let's see the awesome part. You're all good.
Going to go here. X is therefore going to win, so the value of this board is going to be a 1. Now, since there's only one way logically to get from this configuration to this one, we might as well call the value of this board by transitivity 1. And so O probably doesn't want to go there, because that's a pretty maximal score, and O wants to minimize. Over here, though, if O goes bottom middle, well, then X is going to go top left, and now no one has 1, so the value of this board is thus 0. We might as well treat this as 0, because that's the only way to get there logically. So now O, more mathematically and logically, can decide, do I want an endpoint of 1 or an endpoint of 0? Well, 0 is probably the better option, because that's less than 1, and thus it's the minimal possibility. So O is going to go ahead in the bottom middle and at least force a tie. And so that's where you see evidence where if you humans are ever losing the game of tic-tac-toe, you have not followed their logic. But you could probably do it if there's just 2 moves left. But the catch is, let's go ahead and sort of rewind to 3 moves left. Here there are 3 blanks, and I've kind of zoomed out. The catch is that the decision tree gets a lot bigger the more and more moves that are left. It gets sort of bigger and bushier in that it's essentially doubling in size and width. And that's great if you have the luxury of writing it down on a piece of paper, but if you're doing this on your head while playing against a 5th grader, if I may, you're probably not drawing out all of the various boards and configurations trying to play it optimally. You're going with some instinct. And your instinct.
Oh.
No, Kenny.
Well, thanks, Jim. I don't know if she can say.
Kenny.
Can you say hi?
Uh.
You want to say hi?
What?
Well, why?
Because
Oh. Mommy?
yeah.
Oh. Well, I don't know.
Now, Mommy gives her magnet.
Do you want her? Oh.
I want to.
You want me?
Yeah.
Well, I guess. Well, I don't know.
Things might not be aligned with an algorithm that is tried and true, Minimax, that will ideally get you to win the game, but at least will get you to force a tie if you can't win. But tic-tac-toe is not that hard. I mean, how many different ways are there to play tic-tac-toe? We could write a computer program to pretty much play tic-tac-toe optimally. We could use code like this. If the player is X, for each possible move, calculate the score for the board at that point in time, and then choose the move with the highest score. So you just try all possibilities mathematically, and then you make the decision. Most of us in our heads are not doing that, but we could. Else, if the player is O, essentially do the same thing, but choose the minimal possible score. So that's the code for implementing tic-tac-toe. How many ways are there to play tic-tac-toe, though? Well, 255,168, which means if we were to draw that tree, it would be pretty darn big, and it would take you quite a bit of time to sort of think through all those possibilities. So in your defense, you're maybe not that bad at tic-tac-toe. It's just harder than you thought as a game. But what about games with which we might, as adults, be more familiar? Well, what about the game of chess, which is often used as a measure of like how smart a computer is, whether it's Watson back in the day playing against it or something else?
No.
Well, if we consider even just the first 4 moves of tic-tac-toe, whereby I mean black goes and white goes, and then they each go 3 more times, so 4 pairwise moves, how many different ways are there to play chess? Well, it turns out 85 billion just to get the game started. And that's a lot of decisions to consider and then make. How about the game of Go, if familiar? Consider the first 4 moves, 266 quintillion possibilities.
I don't even know.
And
what the
this
game
is
goes,
where we
so.
sort of, as humans, and even with our modern PCs and Macs and phones, kind of have to throw up our hands because I don't have this many bytes of memory in my computer. I don't have this many hours in my life left to actually crunch all of those numbers and figure out the solution. And so where AI comes in is where it's no longer as simple as just writing if, else's, and loops, and no longer as simple as just trying all possibilities. You instead need to write code that doesn't solve the problem directly, but in some sense indirectly. You write code so that the computer figures out how to win, perhaps by showing it configurations of the board that are a good place to be in, that is promising, and maybe
Oh, just so you know, I don't know if anybody else cares, but apparently this is the game Go. I have no idea how to play this. I don't know anything about this, but I did think that was interesting. Oh, how do I zoom out? But yeah. Anyways. Oh, that's the not. I clicked the wrong thing. Oh, okay.
showing it boards that it doesn't want to find itself in the configuration of, because that's going to lead it to lose. In other words, you train it, but not necessarily as exhaustive. And this is what we mean nowadays by machine learning, writing code via which machines learn how to solve problems, generally by being trained on massive amounts of data, and then in new problems looking for patterns via which they can apply those past training data to the problem at hand. And reinforcement learning is one way to think about this, in fact. And in fact, we as humans use reinforcement learning, which is a type of machine learning, sort of all of the time. In fact, a fun demonstration to watch here involves these here pancakes. So in fact, let me go ahead and pull up a short recording here of an actual researcher in a lab who's trying to teach a robot how to make, how to flip pancakes. So we'll see here in this video that there's a robot that has an arm that can go up, down, left, right. This, of course, is the human, the researcher. And he's just going to show the robot one or more times like how to flip a pancake. And crosses his fingers, and okay, seems to have done it well. Does it again, not quite the same, but pretty good. And now he's going to let the robot just try to figure out how to flip that pancake after having just trained it a few different times. The first few times, odds are, the robot's not going to do super well because it really doesn't understand what the human just did or what the whole purpose of. But, and here's the key detail with reinforcement learning, behind the scenes, the human is probably rewarding the robot when it does a good job. Like better and better it flips, the more it gets rewarded, as by like hitting a key and giving it a point, for instance, or giving it the digital equivalent of a cookie. Or conversely, every time the robot screws up and drops the pancake on the floor, sort of a proverbial slap on the wrist, a punishment so that it does less of that behavior the next time. And any of you who are parents, which by definition today many of you are, odds are, whether it's not this or maybe just verbal approval or reprimands, have you probably trained children at some point to do more of one thing and less of another. And what you're seeing in the backdrop there is now just a quantization of the movements, x, y, and z coordinates, so that it can do more of the x's and the y's and the z that led it to some kind of reward. And now after you're up to some 50 trials, the robot seems to be getting better and better, such that, like a good human, we'll see if I can do this without embarrassing myself, can flip the thing.
God damn, why do you flip it so many times? Okay. Jesus.
So we've seen then how you might reinforce learning through that kind of domain. Let's take an example that's familiar to those of you who are gamers. Anytime you've played a game where there's some kind of map or a world that you need to explore, up, down, left, right, maybe you're trying to get to the exit. So here, simplistically, is the player at the yellow dot. Here, for instance, in green is the exit of the map, and you want to get to that point. And maybe somewhere else in this world, there's a lot of like lava pits, and you don't want to fall into the lava pit because you lose a life or you lose a point, or there's some penalty or punishment associated with that. Well, we, with this bird's eye view, can obviously see how to get to the green dot, but if you're playing a game like Zelda or something like that, all you can do is move up, down, left, right, and sort of hope for the best. So let's do just that. Suppose the yellow dot just randomly chooses a direction and goes to the right. Well, now we can sort of take away a life, take away a point, or effectively punish it so that it knows, don't do that.
I don't know if you're asking if I play Roblox or if you're asking GM if he plays Roblox, but I don't. There was a lot of stuff, bad stuff that happened with Roblox, so our kids don't play, used to play it, but after a bunch of stuff happened with that, we don't play it anymore. So I don't know, I don't recommend playing Roblox anymore because the people that made it aren't being careful with it, but yeah, sorry about that.
And so long as the player has a bit of memory, either the human player or the code that's implementing this, just with a dark red line, that means don't do that again, because that didn't lead to a good outcome. So maybe the next time the yellow dot goes this way, and then, didn't realize that that's actually the same lava pit, but that's fine. Use a little bit more memory and remind me, don't do that because I just lost a second life in this story. And maybe it goes this way next time, now I need to remember, don't do that. But effectively, I'm either being punished for doing the wrong thing, or, as we'll soon see, being rewarded for doing more of the successful thing. And just by chance, maybe, I finally make my way to the exit in this way. And so I can be rewarded for that. Now I got 100 points, or whatever it is, the high score. So now, as per these green lines, I can just follow that path again and again, and I can always win this game. Kind of like me nowadays, like 30 years later, playing Super Mario Brothers, because I can get through all the warp levels, because I know where everything is, because for some reason that's still stored in my brain. Is this the best way to play?
So
Am I
he
as good
Mario.
at Super Mario Brothers as I might think? What's bad about this solution? Yeah.
You don't find the best result.
Yeah, I've moved many more times than I need to, and just for fun today, what grade are you in? 7th grade. Wonderful. So now 7th grade observation is like exactly that we could have taken a shorter path, which is essentially that way, albeit making some straight moves. And so we're never going to find that shorter path. We're never going to get the highest score possible if I just keep naively following my well-trodden path. And so how do we break out of that mold? And you can see this even in the real world. Another sort of personal example is I'm the type of person, for some reason, where if I go to a restaurant for the first time, I choose a dish off the menu and I really like it, I will never again order anything else off that menu other than that dish because I know it is good. But there could be something even better on the menu, but I'm never going to explore that because I'd sort of fixed in my ways, as some of you from the smiles might be too. But what if we took advantage of exploring just a little bit? And there's this principle of exploring versus exploiting when it comes to using artificial intelligence to solve problems. Up until now, I've just been exploiting knowledge I already have. Don't go through the red walls, do go through the green walls. Exploit, 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 and I will get to a final solution. But what if I just sprinkle in a little bit of randomness along the way, and maybe 10% of the time, as represented by this epsilon variable, I, as the computer in the story, generate a random number between 0 and 1, and if it's less than that percent, which is going to happen 10% of the time, I'm going to make a random move instead of one that I know will get me closer to the exit. Otherwise, I'll indeed make the move with the highest value. Now, this isn't going to necessarily win me the game that first time, but if I play it enough and enough and enough and insert some of this randomness, I might very well find a better solution and therefore be a better player, a better winner, overall. If I just 10% of the time ordered something else off the menu, I might find that there's an amazing dish out there that otherwise I wouldn't have discovered. And so indeed, using that approach, can we finally find a more optimal path through the maze, as was shorter there, presumably therefore maximizing our score and doing even better than we might have by just exploiting the same knowledge. So you can see this even in the game of Breakout, especially if you write a solution in code to play this game for you. Let me go ahead and pull up another video recording of an AI playing Breakout. And what this AI is doing is essentially figuring out, maybe more intelligently than you or I could, how to play this game optimally. And what we'll see here is that, just like the pancake flipping robot, there's some notion of scoring and rewards and penalties here. So like right now, the paddle's just doing random stuff. It doesn't really know how to play the game yet. But it realizes after 200 episodes that, oh, my score goes up if I hit the ball, and it goes down equivalently if I miss it. And it's still a little twitchy. It doesn't quite understand what it's supposed to do and why. But if you do it again and again and again, and it's rewarded and or punished enough, you'll see that it's...
Yeah, I guess, yeah, I guess I'm about to go. Alright. I'll probably get back to this in a second, but I'm going to have to stop for now. So, I'm sorry. Got things I got to do. But, I'll be back to finish once I get back. So, I got to hurry. But, yeah, I'm going to stop for now and then continue it in a second. Okay, well, this kind of sucks, but I'll pause for a second, so I'm back to it.
Starts to get...
And then, I guess my thing has... Oh, no, it doesn't have a delay. Okay, never mind. Alright, here we are.
Pretty good, and closer to what a good human might do.
After
But here's where the algorithm gets a little creepy. If you let it play long enough, or if you and I, the humans, play long enough, you might find a certain trick to the game. I dare say the AI becomes a bit scarily sentient, in that, turns out, if you're smart enough to break through that top row, you can let the game just play itself for you and maximize your score without even touching the ball. Something that I do find a little creepy, that it just figured out how to do that without being told, but it's just a logical continuation of rewarding it for good behavior and punishing it for bad behavior. So that next time you have an occasion to play Breakout, consider that kind of strategy as opposed to doing more of the work yourself. Let the computer do it for you instead. Well, what else is there to consider in this world of AI in the context of machine learning? Well, there's specifically a category of learning that's supervised. And we've been using this for years. And in fact, our first example of spam early on was certainly supervised. Why? Because it was you and I who was like putting the email into the spam folder. And to this day, maybe once a day, I hit the keyboard shortcut in Gmail to say, this is spam. You should have caught this. And that is training Google's algorithm further, assuming it's not just little old me, but maybe thousands of people tagging that same kind of email as spam. That's supervised learning, and that there's a human in the loop doing at least something. So spam detection might be one of those. But the catch is that labeling data in that way manually just doesn't scale very well. That would be akin to having someone at Google or Microsoft labeling every email, or someone at Netflix doing the same for all of the videos out there. It's expensive in terms of human power, and there's certainly problems out there with so much data. It's just not realistic for humans to label millions of pieces of data, billions of pieces of data. We've got to move to an unsupervised model. And so this is where the world starts to consider deep learning, solving problems using code whereby you don't even have humans in the loop in quite the same way. And neural networks, inspired by the world of biology, are sort of the inspiration for what is the state of the art, even underlying today's rubber duck, and more generally these things called large language models like ChatGPT and the like. So here, pictured somewhat abstractly, is a neuron, and it's something in the human body that transmits a signal, say from left to right, electrically. And if you have multiple neurons, you can intercommunicate among them so that if I think a thought, then I know how to raise my hand because some kind of message electrically has gone from my head to this extremity here. So that's, in essence, what I remember from 9th grade biology. But as a computer scientist, we sort of abstract all of this away. So instead of calling these two neurons, drawing them as neurons, let's just start drawing neurons as these little circles. And if they have connective tissue between them of sorts, we'll just draw a straight line, an edge between them. So this is what a computer scientist would call a graph. If you have two such neurons over here leading to one neuron here, you can think of this as being like maybe two inputs to a problem and now one output there too. We can represent the notion of problem solving, which is what CS50 and intro courses more generally are all about. So let's solve a problem with a neural network without necessarily training it in advance, just letting it figure out how to answer this question. Here's a very simple two-dimensional world, XY grid, and here are two dots. And the dots in this world are either blue or they are red, but I have no idea yet what makes a dot blue or red. However, if you train me on those two dots, I bet I could come up with predictions, especially if you let me label this world in terms of x coordinates on the horizontal, y coordinates on the vertical, and then you know what, we can think of this neural network very simply as representing the x coordinate here, the y coordinate here, and the answer I want to get is quote unquote red or blue, or 0 or 1, or true or false, however you want to think of the representation. So how do I get from a specific xy coordinate to a prediction of color if I only know the coordinates? Well, from the get-go, maybe the best I can do is just divide the world into blue dots on the left and red dots on the right, a best fit line, if you will, based on very minimal data. Of course, if you give me a third dot, it's going to be pretty easy to realize that I was a little too hasty. That line is not vertical, so maybe we pivot the line this way, and now I'm back in business. Now I can predict with higher probability, based on XY, what color the next dot will be. You give me enough of these dots, I can come up with a pretty good best fit line. It's not perfect, but here's a hint at why AI is not perfect, but 99% of the time, maybe I'll be able to predict correctly, and I can do even better if you let me squiggle the line a little bit and maybe make it more than just a simple slope. So what is it we're really doing with implementing this neural network, albeit simplistically with just 3 neurons? Well, essentially, we're trying to come up with 3 values, 3 parameters, an A, a B, and a C. And what do those represent? Well, really just a solution to this formula. That there line we drew can be represented, if you think back to like high school math, with a formula along these lines, whereby it's A times X plus B times Y plus some constant C. And we can just arbitrarily conclude that if that value mathematically gives me a number greater than 0, predict it's going to be blue. Otherwise, predict it's going to be red. We can sort of map our mathematics, just like with tic-tac-toe, to the actual problem we care about by defining the world in this way. And so if you give me enough data points, I can come up with answers for that A, that B, that C, the so-called parameters in neural networks. Now in reality, neural networks are not composed of like 3 neurons and a couple of edges. They look a little something more like this, and in practice, they've got billions of these things here on the screen, in which case, pretty much every one of these edges represents some mathematical value that was contrived based on lots and lots of training data. And whereas I, the computer scientist, might know what these neurons over here represent, because those are my inputs, 3 in this case, and I, the computer scientist, know what this one represents at the end, if you sort of took the hood off of this thing and looked inside the neural network, even though there'd be millions, billions of numbers going on there, I can't tell you what this neuron represents or why this edge has this weight. It's because of the massive amount of training data that's just how the math works out. And if you feed me more data, I might change some of those parameters more. So the graph ultimately might look quite different, but my inputs and my outputs are going to be what I use to solve that there problem. So if you want to predict like rainfall from humidity or pressure, you can have 2 inputs giving that one output. An advertising dollar spent in a given month, that might predict sales by just having trained, again, on such volumes of data. And when we get now full circle to something like CS50's rubber duck and large language models like Claude and Gemini and ChatGPT, what's really happening, and this is all hot off the press in recent years, screenshotted here are some of the recent research papers that have driven a lot of this advancement in recent years. you have, from OpenAI, say, a generative pre-trained transformer, which is a lot to say, but there's the GPT in ChatGPT, and essentially this is a neural network that's been trained on large volumes of textual information that gives us the interactive chat feature that we have in the class, and we all have more generally in ChatGPT itself. So an example of what is actually happening underneath the hood of these GPTs. Well, here's a paragraph that up until recent years was kind of a hard paragraph to end with the ... Massachusetts is a state in the New England region of the northeastern United States. It borders on the Atlantic Ocean to the east. The state's capital is ... Now, most anyone living in Massachusetts probably knows that answer, but if this AI has just been trained on lots and lots of data, there's probably a lot of people who say Massachusetts in part of a sentence, and then the answer, which I won't say yet, is in the other part of the sentence. But in this example, given that the question we're asking is sort of so far from some of the useful keywords, up until recently, this was a hard problem to solve because there was so much distance. Moreover, there's these nouns that are being used to substitute for the proper noun, like we suddenly start calling it a state, we call it a state down here, and it wasn't necessarily obvious to AIs that we're talking about the same thing, as if it were just city, comma, state, where you'd have much more proximity. So in a nutshell, what we now do, especially to solve problems like these, is we first break down a sentence or the training data or input alike into like an array or a list of the words themselves. We come up with a representation of each of these words. For instance, the word Massachusetts, if you encode it in a certain way, is going to be represented with an array or vector of numbers, floating point values, so many so that the word Massachusetts in one model would use these 1,536 floating point numbers to represent Massachusetts, essentially in an n-dimensional space. So not just an xy plane, but somewhere sort of virtually out there. And then, and this has been the key to these GPTs, an attention is calculated based on all of that data, whereby in this picture, the thicker lines imply more of a relationship between those two words. So Massachusetts and state is inferred as having a thicker line, a higher attention from one word to the other, whereas our A's and our is's and our thes have thinner lines because there's just not as much signal to the AI as to what the answer to this question is. Meanwhile, when you then feed that sentence, like the state's capital is, one word per neuron here, the goal is to get the answer to that question. And even here, this is way smaller of a representation than the actual neural network would be. But in effect, all these LLMs, large language models, are just statistical models. Like, what is the highest probability word that it should spit out at the end of this paragraph based on all of the Reddit posts and Google search results and encyclopedias and Wikipedias that it's found and trained on online? Well, the answer hopefully will be Boston. But of course, 1% of the time, maybe less than that, the answer might not be correct. And even CS50's own duck is fallible, even though we've written lots of code to try to put downward pressure on those mistakes. And those mistakes are what we'll call, lastly, hallucinations, where the AI just makes something up, perhaps because some crazy human on the internet made something up and it was interpreted as authoritative, or just by bad luck because of a bit of that exploration, 10% of the time, 1% of the time, the AI sort of veered this way in the large language model, in the neural network, and spit out an answer that just, in fact, is not correct. And so I thought I'd end for today on this final note, a poem with which many of us might have grown up from Shel Silverstein here, about the homework machine, which years ago somehow sort of predicted the state we would be in with these AI machines. He said, "The homework machine, oh the homework machine, most perfect contraption that's ever been seen. Just put in your homework, then drop in a dime, snap on the switch, and in 10 seconds time, your homework comes out, quick and clean as can be. Here it is, 9 plus 4, and the answer is 3. 3? Oh me, I guess it's not as perfect as I thought it would be." This then was CS50. See you next time.
I have the book. I want another book.
Because artificial intelligence isn't perfect. It'll never be perfect, but it's 99% accurate. It's like, so, but I guess the real question is not being 99% correct.
Not as good as you're 99%.
Yeah, but better than the average human. Yeah, that's crazy.
Are you better than the average AI then?
Oh yeah, most definitely. But yeah, so so basically what AI does is whenever you tell it a sentence, it takes every single word and puts those into code, into binary form, and then searches through what information it does have. If it's connected to the internet, then it's all the internet. But it traces to each and every word to figure out if these words go together more often. So like the useless words, when you say like is, the, a, you know what I mean? But when you say something like Massachusetts and state, it'll go and find and see how many times those words go together, and then it'll target the words that link together more than the other words that don't, so it can use the information that it actually needs out of what you're saying.
Like the search engines.
Yeah, so like, even though it is taking in every bit of information that you're saying and giving it, but it is searching for the most used information that it has in its data. You know, like which words go together more, which words do people search for more that go together, and then from there it tries to determine what you're trying to say.
Like how I was pulling certain sentences from messages and stuff.
Yeah. And all it does is it's trial and error. So every time it gets something wrong, it basically marks that down like, okay, that's the bad way to go.
Okay.
And then every time it's right, then it writes, okay, that's the good way to go. But the other thing that AI does is, additionally from that, it also still tries to find other answers in case there's a better answer. So even though it could have been right for one situation, it still attempts at different situations just in case, to see if that situation will be a better outcome. You know what I mean? But yeah, it's pretty neat. And apparently building AI and coding is super easy because they did all the work for you. So you can create your own AI, whatever. You just have to implement the original AI coding that was built by somebody else. You just import it, like you import a lot of things. So, and you can create your own AI in coding. And like they have an AI that's a duck that they use, and all they have to do is they import the AI like data, and it literally pulls the physical coding of that AI from, I guess, specifically where you'd want to pull it from. Like I did it on one of these, I could show you. And like there's not really, because it's already been done, there's not really, you don't really have to do anything anymore unless you create like AI from scratch. But this is literally, let's see, what was it called? I think it was like called Chat. This thing's taking forever. Okay, so here it is. So, in this one, this is all that they really do to create AIs nowadays. Like this little duck AI that they made is, since they already did the coding to design the AI, you take the open AI and import it, since that's already the coding for it, and it uses that coding and forces it into this coding, and then you use their keywords, and you literally just, I mean, this code is created to where you're telling it to, you know, prompt the user for a response. And then this part is the definition of what the system prompts. This is what you're telling it to do. Limit your answer to one sentence. Pretend you're a cat. very basic. You like tell it exactly what you want it to be like, how you want it to function. Like their duck one, it was like 5 sentences. Like they're like, you're a duck. Don't directly answer questions. Don't give people the exact answer, and help people find the answer themselves. Like stuff like that. But and then you just you put some of this basic stuff. So this is the model AI is I guess GPT. So I guess it has this link to Chat GPT, but it's not, because Chat GPT is its own thing. But it's GPT-5 is the one that they were using, and then this is where you put response, and then input user prompt, where it uses this variable for that, and then instruction system prompt, and these are the instructions right here. So you just define these variables, you put them in here, and then you put print response output text, where you're just telling it to, first prompt for an input, then use the system prompt to determine your response, and then what model you are wanting to use, and then print the output. It's not even like anything to it though. It's like
super simple.
yeah, but it's only simple because this is just one of those things where this is what you do in a lot of coding. And so in Python, you don't have to do this because it's already in that, but you can do it in Python because this is technically Python. But usually you don't have to do this in Python because Python already has a bunch of stuff already imported into it. Whereas like the other one I was using, C, has nothing imported into it. So every time you do any kind of coding, you have to import something. But Python already has like the basic stuff imported. So then whenever you get to this, where you need something that isn't built into Python's original system, then you have to import it. And OpenAI is already in it, so that's all you have to do is import it, and then you can create your own AI. It's like crazy. I don't know.
Is it an AI with a back door?
Huh?
Is it an AI with a back door?
With a back door.
Like anyone could get into it and change it?
I don't know.
You're not there yet?
Well, no, not really, because all you're doing is you're importing the coding from this.
The
I mean,
initial coding to create the AI, so you can establish on top of it, right?
yeah.
Insert it as needed.
Yeah. It's like in the old C, you had to import strings. Because you couldn't write strings, you could only write characters. A character is a single, like, alphabetical letter. But a string is alphabetical letters put together, where you have either a word or a sentence or anything that's a length of things. A character is one single input. So they had to, you either had to write it out the long way, which was like character star, which creates a pointer to a space that links the rest of the words to the rest of the characters together. Or you could do the short version where you just tell it that you're creating a string, but you have to import that's in there, and that would bring that coding to it, but you'd have to just call that function from that import. So that's all you're doing with this. Same thing is technically that coding is in here, and you're pulling that coding into it. No, but you could look into OpenAI and see what's in that coding.
Yeah.
But yeah.
I'm in pain.
Sorry.
That's totally your fault.
I didn't say it was my fault.
Why are you apologizing then?
Because I feel bad for you.
I love you too.
I'm sorry, mofo.
You sorry, son.
Alright, well, I finished the artificial intelligence. Not that I had to, but it was interesting. It was super easy. Did he have people that were in like 5th and 7th grade in there?
What?
Well,
In
like,
his-
because he was talking about this one thing where he's like, does this look like it was written by a 4th grader, or does this look like it was written by AI? And it was supposed to be AI interpreting or pretending to be a 4th grader. And so people were, 60% of people were able to tell the difference. And it was like, well, why is that? And then one of the kids raised his hand, and he's like, because that's how I would say something. And he's like, oh, what grade are you? And he's like, 5th grade. He's like, oh, you're 5th grade. So this is how you would say something. So the other one must be this must be the AI. And yeah, that's how he.
That's wild.
He's like, because that's how I would talk, not a 4th grader.
Is it online that he's answering that with, or is it in his classroom?
Yeah, it's on this thing.
It's,
He's in the class.
Spam or non-spam.
Oh.
See, there's a bunch of this is a real class, and I don't know how many.
In Harvard.
Apparently, that's who was talking. I can't see the people. I can only see the back of their heads. But there have been situations where he's pointing at people, and he points up there, and
Oh, there are.
it's
So UT offers courses that you can go in and is free online course. This is a free course, so they're probably locally there, and classes and stuff can sign up for it too. Sativa's done school stuff like that where she signed up for it, and then you can find it online for UT.
The Historical Sanders Theater. Okay, this is it. I want to see what it looks like. This is what it looks like.
That's beautiful.
Dude, that is way cooler than I thought. It was like a hallway or something. I wasn't expecting it to look like that.
Nice.
That is cool.
That
Look
is
how many
pretty.
people you can fit in there. It's a theater room basically.
Yeah, you could tell by the backdrop. Look at the back. It's so gorgeous.
Yeah. Well, when he's in there, it looks
So
amazing.
good.
I'm like, that place looks freaking beautiful,
That's
dude.
that architectural drip.
Dude, it is. It looks so clean and man, it looks good.
One day,
Dang. Look, that's the second
Summer
floor.
home.
God dang.
all wood, everything wood grain.
All right, see, there's the building. That's so cool. Oh man, we need to travel.
So pretty, for real.
Dude, look how many people is in this
I
one.
have to cough up and get a minivan because driving around in that Escalade gonna get expensive.
I don't know, minivan's gonna be much cheaper. Yeah, look at
Yeah,
this one.
regular gas is cheaper than premium by a ton.
Yeah.
And then you got a 6-cylinder compared to 8-cylinder. Huge difference.
You get a 4-cylinder at that point.
I mean, might as well if we're gonna go travel with the
Might as
kids.
well get a Miata at that point.
How are we gonna fit the kids in a Miata?
Oh, they're gonna have to go get their own cars.
Just strap them to the roof.
Or do just throw them in the
Put
trunk.
a car roof rack up there and put a camera. Everybody up top.
I
Don't-
was talking about a convertible though.
Still, we have 4 kids. How are we gonna fit them all in a Miata?
Oh, just stack them up.
We want the extended cab Miata.
Duh.
They don't make those. They will now.
Oh, that's so cool. That's exciting.
What is
Okay.
a red flag warning?